Welcome! Today we're going to jump into partial derivatives. Real functions of several variables. You should be familiar with functions f of one variable. So f of x. The tools of calculus were useful because you could sketch the graph, y equals f of x. You could find max and min. You could analyze the slope of f by calculating the first derivative. You could find approximations of f using the Taylor series, although you probably haven't done that. It's a good idea to look it up. And you could find solutions to the equation f of x equals 0. All right, so just because you haven't seen Taylor series, and now it's not really a part of this course, but I'll just show you an example of a Taylor series for sine of x. So let's just take this about x equals 0, and we'll take, I don't know, 8 terms. So it looks like this, right? So you can represent sine x as an infinite series. Now I've chopped it off here after the 8th term, but if I just take this and then give x a value, so say x equals, now I need to choose something close to 0, otherwise it's a bad approximation. So for example, if I take 0.5, okay, I put that in memory, and let's evaluate this. So we've got 0.479 for that approximation, and that's an approximation because it's chopped off. But let's also take sine of 0.5. Okay, so you can see these are extremely close. So much so that it's beyond the 6th decimal place where they're different. So let's have a look. So it's way out here where they start to be different. So that's a really good approximation of sine of x. So if that's taken as an infinite series, then those are exactly equal provided that x is within the radius of convergence. All right, so these are things that you could look up and a bit beyond what I'm showing you here. So back to this. Many familiar formulas are essentially just functions of more than one variable. For example, the volume of a box is a function of its width, its height, and its depth. So V of W, H, and D is the product of those three. That gives you the volume of the box when it's a rectangle or rectanguloid. And the profile of a vibrating string is a function of time and position along the string. So by hand, because I promised you a lot of hand calculations and hand drawings, so let's draw something by hand. So if we have x and we have f of x and t, but here let's just think about this initially when t is equal to 0. So we might have a string that starts here, comes up to its amplitude, and then comes back down. Now, if I'm looking at this function f is equal to a sine of x cos of t, then the top of that is the amplitude, that's the height, so that is a, and this down here would be pi radians. So pi radians where it comes back down. Now this is at t equals 0. So if you included time changing and plotted this in 3 dimensions, then it would look like this on the left, all right? But I'm going to take this, and I'm going to display this for you here in Mathematica. So I want to go plot a sine of x cos of t. Now x seems to be in memory. I want to give a value, so let's just choose something simple like a equals 1, amplitude of 1. We'll clear all x, and then we'll plot this. Now pi is 3.14 or so, so let's plot this between 0 and 3.2. All right, but you see t is in blue. Okay, so if I were to put t equals 0, then I could plot this, and you see I have something that looks like what I have here. Okay, so this is your string. All right, so this is your string initially, but then if you let that go and let that bounce back down to the origin, you would get a wave motion with time. All right, so let's clear both x and t, and then I'm going to write manipulate in front of this. And we're going to manipulate this as t goes from 0 to, I don't know, what does this say? It doesn't say anything, so let's go, I don't know, 15 seconds. Yeah, somewhere I think it says 15 seconds. So let's do this now. Okay, so now I can take this bar and change the time. Okay, so as I increase time, and it doesn't quite look right because what I need to do also is include some frame of reference so it doesn't change the bounds. So I'll also put 1 and see if this makes any difference. Okay, so there's my amplitude, and now we can see this changing. Let's also put in -1 because it goes from 1 to -1. So now we can see this changing with time. All right, so it goes up and down. So what you're seeing here then is a plot of this string vibrating with t as your third. So this is t, the t-axis. This is x, and then what we have up here is a z-axis, right? The height of that string. So this is fixed, right? But this, what I've shown you on the left here, is animated as t is moving. All right, so this is a three-dimensional plot of this scenario. All right, let's move on. Consider the volume of a cylinder as a function of two variables. So the two variables are the radius, which will be, in this drawing, this is our radius, and then the height of this cylinder is L, or length. So this is the cylinder, and the volume is, you know, the volume that you see there. All right, but we can also plot V as a function of the radius and the length. So as the radius gets bigger, now that's out here for the radius, and then this axis would be L, and then this axis up here is that volume. So as the radius increases, and as the volume, as the length increases, so does the volume, right? So we can visualize that in two ways, right? Okay, the equation of a plane can be expressed using scalars or vectors. In this section, we'll sketch planes in R3, or so three-dimensional space, and determine their scalar equations. In 3 space, we usually take Z pointing upwards and the XY plane to be horizontal. All right, so if you don't know the convention, here's our axes. We usually put Z up, but now what is this and what is this? Okay, so you use your right hand. So X, Y, Z in alphabetical order. X being the first letter goes towards the Y, the next letter, and then the third letter is Z, so that points up, so that you can draw this any way you like so long as it follows your right hand. So we'll put an X here and a Y here. Okay, so with this point of reference or point of view, we sketch planes. Okay, so let's go ahead and sketch the horizontal plane Z equals 2. So we'll do this. We'll draw our X, Y, and Z. Now, we have Z as a function of X and Y. We know that that's equal to 2. All right, so what this says then, no matter what X is and what Y is, Z is always equal to 2. Now, let's find 2. So 1, 2. Let's put it here. So we have a point 0, 0, 2. Okay, now I want to draw a plane. It's going to be horizontal because remember, no matter what x is and what y is, z is always equal to 2 in this horizontal plane. So I'll do my best to draw that, but you have to use a little bit of imagination. So something like this. Okay, let's move on to the next page. The general equation of a plane in 3 space is given by ax plus by plus cz equals d, with a, b, c, and d fixed real numbers. If the plane is not vertical, so in other words, that happens, it's vertical when c is equal to 0. So if c is not equal to 0, this equation can be rearranged so that z can be expressed as a function of x and y. So when you do that, given that c is not 0, you'd be dividing throughout in this equation by c so that you cancel the c that's in front of the z, and then you would rearrange so that z is isolated on the left-hand side. And so you would get z is equal to minus a over c times x minus b over c times y plus d over c. Okay, and if we call m equal to minus a over c and n equal to minus b over c, then this is what we have, and we call d over c equal to z0, right? Because that's what happens when you have x equals 0 and y equals 0. You get a z value when x and y are both 0. So why not call that z0? So z is equal to a function of x and y, m times x plus n times y plus z0. Right? So that's when you know that c is not equal to 0, or in other words, if the plane's not vertical. The easiest way to sketch the plane by hand is the triangle method. So in the triangle method, we find 3 points that are on the axes because that's really easy to find and to plot. And then we draw a triangle between those 3 points and then imagine the plane that passes through those 3 points. Okay, so let's take, for example, the plane x plus 2y plus z is equal to 4. All right, so what are 3 points on that plane? So when y and z are both equal to 0, well, we would have x equal to 4, and so that gives us a point. So let's write points. We have a point 4, 0, 0. Okay, now when x is equal to 0 and z is equal to 0, what would y be equal to? Right, so if we have these two equal to 0, well then dividing by 2, we'd have y equals 2. So we've got a point 0, 2, 0. Okay, now when x is 0 and y is 0, what's z equal to? Well, z would be equal to 4. So we have 3 easy points on the axes, and that's here, which is, this is the point 0, 2, 0. So the y-axis comes out this way. And then this is the point 4, 0, 0. So the x-axis comes out this way, and then the z-axis comes out this way. Okay, so does this agree with the right-hand rule? X, y, z. So yes, I've just taken the orientation from this way, more like this, right? Like this, so that this is z coming up. So it agrees with that convention. All right, now this point over here is the point 0, 0, 4. Okay, then we connect those, and then we fill in the plane. All right, so that's done here. And of course you could do that in Mathematica, but I won't. Okay, so the triangle method is based on the simple fact that any 3 points that lie in a plane uniquely determine this plane, provided that these 3 points do not lie in a single straight line. it's customary to say the equation of a plane even though it's not unique. Okay, so what do we mean by that? Well, multiplying the equation of a plane by a non-zero constant gives another equation for the same plane. For example, the plane x minus 2y plus 3z equals 4 and minus 2x plus 4y minus 6z equals minus 8 are equations of the same plane. So what's happened here is just taken this one and multiplied that throughout by minus 2. So minus 2 times x minus 2y plus 3z gives us minus 2x plus 4y minus 6z, and that's equal to minus 2 times 4, which is 8. Example 2.2, find the equation of the plane passing through the 3 points 0, 0, 5, 1, 3, 2, and 0, 1, 1. Okay, so now this is not parallel to the z-axis. So note, not parallel to z-axis. In other words, not vertical. And so what do we learn from that? And why do we know it's not vertical? Well, look at the points. I mean, there are various numbers in the x, y, and z coordinates, and so we don't always have this constant relationship between x and y. So it's not vertical. All right, so what you learn then is that since it's not parallel to the z-axis, the coefficient of z is not 0. And likewise, if you have a plane that is not parallel to the x-axis, then the coefficient of x will not be 0. And similarly for y. Okay, so then we know that we can write, so we can put z is equal to, say, m x plus n y, and then plus some, let's call it uppercase D rather than z0. Okay, because why not? So it looks like this. Now, so our job is to use these 3 points to find m, n, and d. All right, so let's get started with that. So the point 0, 0, 5 gives us z is 5. So we have m times 0 plus n times 0 plus d. Okay, so clearly that says that d is equal to 5. So d equals 5. All right, let's use our next point. 1, 3, 2. Okay, so z is 2. X in this case is 1. Y is 3. So n times 3. And then plus d, but we already know that d is 5. So let's rearrange this. That says m plus 3n is 2 minus 5 is minus 3. Okay, let's use our third point, which was 0, 1, 1. So 0, 1, 1 gives us, so z is 1 in this case, so 1 is equal to m times 0 plus n times 1, and then plus 5. Okay, so simplifying this, we have n is equal to 1 minus 5 is minus 4. Okay, so this has given us n, we've got d, the only thing missing is m, but we can use this as simultaneous equations here to solve for m. So let's sub that in. So when we sub in minus 4 for n into this first equation, well, we've got minus 12, right? So we take that minus 12 over to the right-hand side. We have 3 minus 12. Sorry, 3 minus minus 12 is 12 minus 3, so we get 9. So substitution, gives m equal to 9. Okay, so putting all those pieces together, the equation of the plane is 9x minus 4y plus 5 is z. And so here we've got z as a function of x and y. All right. Geographical maps have curves of constant height above sea level, or curves of constant air pressure, isobars, or curves of constant temperature, isothermals. So you can guess now that iso means same. Drawing contours is an effective method of representing a three-dimensional surface in 2 dimensions. So I don't know if you've ever looked at a contour map when you've gone hiking. I think this is for people who go hiking with a compass and something else, right? So what do we call these? ISO height? What's that? ISO elevation, let's call it. All right, so elevation maps. So for example, you might have the top of, let's call it Mount Coolum, because I live next to Mount Coolum. It might look like this, where if you went around it, this would be of constant elevation, and then lower than that might look something like this, and then this would be where that beacon tower is. You know, the top of Mount Coolum. Mount Coolum. Or if you're in Petrie, I don't know what the biggest mountain there around there is, but something similar. So this gives us a way to think about surfaces or functions of 2 variables. Because if you take horizontal slices through those, you get curves in the xy plane, and those can help you visualize that surface in 3D. So let's take a look at this example. Consider the surface z equals x squared plus y squared, sliced by horizontal plane z equals 0, z equals 1, z equals 2, and so on. So if we just sub those values in, we can see that we have various curves in the xy plane, and they are circles, except for this first one, which is a single isolated point, 0, 0. So we've got a point, then we've got a circle of radius 1, then we've got a circle of radius root 2, then we have a circle of radius root 3, then we have a circle of radius 2. Okay, so that would look like this, roughly, right? These would be horizontal slices through that surface, z equals x squared plus y squared. So it gives you a way to visualize that. Okay, so now on the left of the next page, we have 2 surfaces that have circular contours. Now you can see some of the slices here. So z equals 0, z equals 1, z equals 2, and so on. Or in this case, this top one is z equals 4. This one is z equals 2. This looks like z equals 1. Okay, but those intersections of those horizontal planes with the surface give you circles. So what we have here is a plot of z as a function of x and y equal to x squared plus y squared. Right? Similarly over here, z equals 4, z equals 2, z equals 1, I think. But over here we've got z as a function of x and y, and this time it's equal to the square root of x squared plus y squared. Okay, so this one is a cone, and this one, in physics, it would be called a potential well. But I would call it in mathematics a paraboloid. in maths and in physics, potential well. All right, so as the radius increases, the contours are more closely spaced. Okay, now part of me wants to show you here on the computer. In fact, why don't I do that? So I'll just write contour plot. And then we'll put x squared plus y squared. X goes from, say, -3 to 3. Y goes from -3 to 3. Okay, so this plots those contours in color. And now let's do below that a three-dimensional plot. I'll just copy this and write 3D in front of that. So you can see that this is the paraboloid. So this here, I can grab this and look around it, you see? And you can do this too, because I've shown you how to install Mathematica on your machine. So you could and probably should do this too, so you get a feel for this. All right, so let's move on. So example 2.3, draw a contour diagram of f given by f of xy is the square root of x squared plus y squared. So we've kind of already done that. So contours of z equals the square root of x squared plus y squared. So let's just draw a few. So they're just concentric circles. For the various heights, right? And if you don't believe me, let's just take this and we'll just put a square root around this. Okay, I'll just write SQRT and that bracket. And then we'll put that here as well. Okay, so you can see we've got the plot of that. So these look evenly spaced throughout. Alrighty, let's move on to the next page. So we can do this for other surfaces also. So this here is e to the power of minus x squared minus y squared. And that also has circular contours. So in other words, horizontal slices through this give you circles. Example 2.4, draw a contour diagram for z equals x squared plus 4y squared minus 2x plus 1. So it would be a good idea first to complete the square on this one. So we'll take these two parts, pack that together with the x squared, and notice that that is x minus 1 all squared. So we have the equation z is equal to x minus 1 all squared plus 4y squared. So when z is equal to 1, we sub in 1 there, and we have x minus 1 squared plus 4y squared equals 1. So that is an ellipse centered at 1, 0. So let's see if we can put a little sketch in this box as well. So here's x and y axis. So here's the origin. And then, so the ellipse is centered at 1, 0. So let's put that here. And then we've got intercepts, x is 0 and x is 2. And then, let's see. So when we have x equals 1, this part would be 0. And so y squared would be 1 over 4, so y would be plus or minus a half. Okay, so if we put that here, 1/2 there, minus a half here. This is the top and the bottom of that ellipse, so we've got these other 2 points, and then let's just fill in our ellipse. Okay, I've done that by hand. All right, now when z is equal to 2, again, we have an ellipse centered at 1, 0, but our intercepts change. So the x-intercepts are x is equal to 1 plus or minus root 2, and we have x values up here, top and bottom points, y equals plus or minus 1 on root 2, which is about 0.7, right? 0.70 something, I think, from memory. So we would get a slightly bigger ellipse here, because 0.7 is bigger than 0.5. Okay, so the other one was here, so I'll just redraw that. But then this one, about 1.7 on this side, so something like this. And then, so root 2, root 2 is 1.4142135562 and so on. So 1 plus that is 2 point. So we're out here, aren't we? So something like this would be the second one. Okay, then this one is even bigger. All right, so let's move on. A saddle, for example, z is equal to x squared minus y squared, has hyperbolic contours. So on the next page, we're going to see an example. So on the left, we have a three-dimensional plot. Z is equal to x squared minus y squared. And then over here, we've got the horizontal slices through this. Now have a look. So here, when z is equal to 1, we have a horizontal slice, right? So what do you see there? That is a hyperbola there where it's sliced off. Okay, so when z is equal to 1, that corresponds to this curve right here and the one on the other side. Okay, so let's just write that. I'm going to turn the page a little bit. You should too. Z equals 1. Z equals 1. Now, notice when z is equal to 0, now let's use this little template. So when z is equal to 0, we've got x squared minus y squared equals 0. But we can factorize the left-hand side. So factorizing the left-hand side gives us x plus y times x minus y equals 0. Now that is 0 when we have x plus y is 0 or x minus y is 0. So we can take the y over to the right-hand side and then rearrange sides so that that would say x is equal to y, or y equals x. This one would say y is equal to minus x. So putting those two together, we have y equals plus or minus x. And that is these two asymptote lines of the hyperbola, say x squared minus y squared equals 1. Okay, so this is z equals 0, z equals 0. Now let's have a look at this x squared minus y squared equals 1. What I usually do to work out which way the hyperbola goes is I find a point. Okay, so for this one, if we put in y equals 0, then we've got x squared is 1, and so x is plus or minus 1. So this has points plus or minus 1, comma 0. All right, and then I find those, so that's here and here, and then I fill in a hyperbola with those asymptotes, meaning that it tends towards those lines. All right, now z is 2. We've got x squared minus y squared equals 2. So let's find some points of that. So when y is 0, we've got x squared is 2, so x is plus or minus root 2. So we've got points plus or minus root 2, 0. Okay, so that would be there, and then I fill in when I sketch a hyperbola with those asymptote lines. So this is z equals plus 2. This is also z equals 2. Okay, z equals minus 1. So we have x squared minus y squared equals minus 1. And so again, filling in some points, if we put in x is 0, then we've got y is plus or minus 1, or y squared is 1. So this gives us points 0, plus or minus 1. Okay, filling that in, that's up here and here. And so we can label these curves z equals minus 1, down here z equals minus 1. All right, now as a slice through the surface, that's down the bottom, right? That's so through here, I suppose. That's probably the bottom plane if I see that. All right, now z equals minus 2. We've got x squared minus y squared equals minus 2. And so filling in some points, again, we can put in x is 0. And so then we've got y squared is equal to 2. And so y is equal to plus or minus root 2. Okay, filling in some points, that's there and there. So these correspond to z equals minus 2, z equals minus 2. Okay, so you could take this, sketch all of these curves, and then from that realize what this looks like, right? So this is a way to visualize a three-dimensional surface by plotting it by hand. Example 2.5. Okay, so this will be a pretty full page. I'm going to focus on these two because I can't fit the whole thing in there. So maybe you can write an extra page if you like, if you want to do all of them. Sketch the contour diagram for z equals 9x squared minus 4y squared plus 2 with these contours. Okay, so let's start with that. So for z equals 9x squared minus 4y squared plus 2, I'll underline that. When z is equal to, let's see, minus 2, we are looking at, now if that's minus 2 over here, we can take this over. So we have 9x squared minus 4y squared equals minus 2 minus another 2 is minus 4. Okay, let's see, what is this? That is hyperbola. We've got a difference. There's squares in each one. So we have, let's find some points. But first, maybe we want to find asymptotes. So asymptotes occur when the right-hand side is equal to 0. And so if we factorize the left, we would have 3x plus 2y equals 0 and 3x minus 2y equals 0. So that gives us asymptotes. Let's see, dividing by the 2, we'd have y equals plus or minus 3 over 2x. These are our asymptotes. Now, applying our trick that we used before, when x is equal to 0, cancel the minus 4s, and we've got y squared equals 1. So points, it has points among many more, 0 plus or minus 1. Okay, so down here I'm going to sketch by hand. X and Y axis. Okay, let's find our asymptotes first. So these, so 1.5 is 3 over 2, so a bit steeper than a slope of 1, something like this. And this for our two asymptotes. Okay, let's find these points. So x is 0, y is plus or minus 1. So if we put 1 in there, minus 1 there, here are our points. Now it's got to fit in there. So something like this, heading towards those asymptote lines. All right, and so that is z equals minus 2. Likewise there. And so this one here will be z equal to plus 2. So z equals plus 2 gives 9x squared minus 4y squared is equal to 0 because the 2's vanish on both sides. Okay, so the asymptotes here are z equals 2. All right, let's move on to z equals 6. Now, so we would have, looking at this equation, if we had 6 over here, 6 minus 2 is 4, so that gives us a plus 4 on the other side. So 9x squared minus 4y squared equals plus 4. So then, if we have y equals 0, so let's find some points. If y is equal to 0, then x squared is 4 over 9. So x is plus or minus 2/3 and y is 0. Okay, so let's put that, say, there, and we'll fill in an asymptote. Fill in a hyperbola tending to that asymptote. And so this is z equals plus 2. Okay, now the last one there is z equals 10. So when z is equal to 10, if we have 10 on the left-hand side of this equation, taking that 2 over gives us minus 8, doesn't it? So, is that right? No. Plus 8. 10 minus 2 is 8. Okay. So 9x squared minus 4y squared equals 8. Okay, so that has points. If we put in 0 for y, then we've got x squared is 8 over 9. Taking square roots, the square root of 8 is 2 root 2. So 2 root 2 over 3. And we've got plus or minus that, and then 0 for y. All right, so now what is 2 root 2 numerically? It's twice 1.41. So 2.82 or 2.83, about 2.8. Oh, and let's divide by 3, right? So 0.94 or so. All right, so anyway, so it's going to look like this, tending towards that asymptote. Okay, and so from that, you can imagine a saddle where these are the various heights. So for positive heights, they're coming around like this, and for negative heights, they're going this way. Okay, now in this little box here, let's do the next one for z equals x squared. Okay, so these are easier because we have a bunch of lines. So z equals 0, well, that just gives us x equals 0. So when z is equal to 1, we have x is plus or minus 1. Now when z is equal to 2, we've got x is equal to plus or minus root 2. When z is equal to 3, we have x is equal to plus or minus root 3. And when z is equal to 4, we have x equal to plus or minus 2. Okay, so let's sketch x, y. Now, what do these look like? Well, they're lines, they're vertical lines, right? So we've got this, then we've got these two. So this is x equals plus or minus 1, which is z equals 1. Okay, then out here, we've got other lines. So this is z equals, because I put this at 2, right? So that's z equals 4, and so on. All right, so from this, how do we interpret a three-dimensional diagram? So what that looks like, if we put x there, y there, and z there, well then these the slices are lines parallel to the y-axis. So what I want to draw is three-dimensional. It's hard to do, but I'm trying to draw vertical slices that are hyperbolas and horizontal slices or contours that are lines. Right, so hard to do. Okay, something like this. Okay, great. Moving on to the next page. Note, contour diagrams of functions whose graphs are planes consist of equidistant parallel lines. So we just saw some parallel lines. But planes have contour diagrams that look like that too. It's possible to construct the plane itself from its contour diagram provided the contours are labeled. Let the plane be z equals mx plus ny plus c. Any point in the plane, so a point x0, y0, z0 gives c. To find m, consider moving along the plane in the positive x direction between two contours. Calculate the change in z, delta z, between the two contours and the change in x, delta x, as you move from one contour line to the next. Move in the x direction only, i.e. in a plane y equals c. Then m equals delta z on delta x. Similarly, take a plane c, x equals c, and move in the positive y direction to calculate delta y. Then n is equal to delta z on delta y. Okay, example. Find the plane given by the following contour diagram. Now here we have a typo, so fix this in your copy. That 5 should be a 3. Okay, so first note that delta z, so the change in z here between z equals 0 and z equals 1 is 1. So moreover, if y equals 0, then from 2x plus y equals 3 and 2x plus y equals 2, we obtain x is 3 over 2 and x is 1 respectively. So delta x is the difference of those, which is minus half. It follows then that m is equal to delta z on delta x, which is minus 2. Similarly, we can get a change in y as minus 1, and so it follows that n is equal to delta z over delta y, which is minus 1. So putting those two things together, we have m is minus 2 and n is minus 1. So then that tells us, according to that, we have z equals minus 2x minus y and then plus c. So we've got to work out the c in this case. And so continuing on to the next page, to find c, we see that we have a point 1, 1, 0. It's on the plane and satisfies 2x plus y is equal to 3. So this point must be on the plane, and that leads to, subbing that in, it leads to c equals 3. So that gives us z is equal to 3 minus 2x minus y. All right, moving on to the next example, 2.7. Find the plane with slope 6 in the direction x, in the x direction, and 4 in the y direction, which passes through the point 154. Okay, z is equal to mx plus ny plus c. We've got m is 6 and n is 4. So we can write this z equals 6x plus 4y, and then we've got to work out c. So if we just sub in, so that dot represents times in this case, so if you want to change that to times, that's okay. So subbing in the values of this point, we've got 1 is equal to 6 times, oh no, 4 is equal to 6 times 1 plus 4 times 5. And then we need a plus c in this as well, which we missed there. Okay, good. So then plus c. All right, so solving this for c, so on the right-hand side, we've got 26 plus c, and then 4 on the left-hand side. So 4 minus 26 is minus 22. Okay, so c equals minus 22, just as we have there. Now, the task of finding or plotting this, let's use the triangle method. So given that z equals 6x plus 4y minus 22, okay, so putting in x is 0 and y is 0, we've got z is minus 22. So points 0, 0, minus 22. And now if we put in, let's see, let's put in z is 0 and y is 0. So then we would get x is equal to 22 over 6. So 22 over 6, 0, 0. All right, so that's between 3 and 4, 22 over 6. All right, next, if x is 0 and z is 0, what y value do we have? So 0 there, 0 there. So 22 over 4 is 11 over 2. Or 5.5, right? So 0, 11 over 2, and 0. So 3 points. Let's find these here. Okay, this is our x-axis. This is our... No, let's make that the y-axis. This is the x-axis. This is a z-axis. Okay. All right, so 22 over 6. We said that's between 3 and 4, so let's put that there. Okay, then we've got 5.5. So maybe that's there. And then this one, minus 22, that would be way down here. Just put that there. Okay, connecting those with a triangle, and now we can visualize that plane. But let's go back and look at this. So this line, because this is on the z-axis down here, so this is a slice through the xy plane. And so this slope of this dashed line here is equal to, I think, what did we say? So that's delta z over delta y, right? And so looking back at, where did I put that page? On the floor. So delta z over delta y is n. And n in this case was equal to minus 1, right? Or no, that was a different example. N in this case was the coefficient of y, and the coefficient of y here is 4. So this is slope 4. Okay, but if we do the same thing with this, so this line has slope 6. Okay, and I'm going to stop right here for now and resume in another video where we'll talk about partial derivatives and tangent planes.